Hello everyone and welcome to the last video of the binary search series. And in this video we are going to solve the problem split array largest sum. Now this is going to be the last problem of this series, and in my opinion this is probably the most interesting problem in this series. So this problem actually uses binary search in a little different way. And how is it different or interesting? It is different or interesting because here we are not going to do binary search on any input given to us. So we do not have any input collection or a data structure where we are going to apply binary search. But what we'll do is we'll try to come up with a range of potential answers. So we'll try to come up with a range in which all the numbers within this range can be potential answers. And then we'll try to use binary search to find the correct answer. So let's not jump ahead. Let's first go through the problem, analyze the problem, and then we'll try to come up with a solution step by step. And we'll step by step we'll try to reach to the binary search solution. So let's go through the problem statement once. And the problem statement states that given an array nums which consists of non-negative integers and an integer m, you can split the array into m non-empty continuous subarrays. So write an algorithm to minimize the largest sum among these m subarrays. So the problem says that we have been given an input array and we have been given a value m, and now we need to break this array into subarrays, into continuous subarrays, such that the number of subarrays is equal to m, and the largest sum among all these subarrays. So each subarray out of these m subarrays will have a sum. So the largest sum among all these subarrays should be minimized. Now let's first try to see that what is the largest and the smallest possible sum. So let's, for the time being, let's ignore the m and let's take this array 7, 2, 5, 10, 8. So what is the least sum possible? Let's ignore m and let's assume that we can break it into as many subarrays as we want. There's no constraint on the number of subarrays. So what is the minimum value of sum, or the least possible sum that we can get, or the least possible largest sum that we can get? Now if there's no constraint on m, then we can minimize the sum by keeping each element in a different subarray, because as soon as you club two elements together in the same subarray, or both the elements will be added and the sum for that subarray is going to go up. Since there's no constraint on m, or we are not trying to optimize the value of m, the most optimal solution would be to keep each element separate, and that's how we can keep the value for each subarray minimized. And also there's no negative numbers in the array, so definitely adding two numbers would give a larger sum. So if we keep each element in a different subarray, then the sub values will be 7, 2, 5, 10, 8. That is the element itself. So what is the least possible largest sum? So even if we keep all elements separate, the answer is going to be 10, because 10, this value cannot be broken down any further, and if 10 is the sole element in a subarray, the sum of that subarray is going to be 10, and we cannot minimize this value further. So the least value possible is 10. What is the maximum value possible? Obviously the maximum value possible is that you club everything into one subarray. There's no different subarray, you've clubbed everything into one subarray and all the numbers get added. So the sum that we are going to get is the highest possible sum. So for this particular array, the highest possible sum is 7 plus 9 plus 14 plus 24 and plus 8, which gives us 32. So the smallest possible sum is 10 and the largest is 32. Now obviously there are going to be many possibilities between these. We can club these two elements, or we can club these three elements, or rather we can club these three elements together and these two elements together. So all these scenarios are going to give me different values, but one thing I can be sure of is that all those values are going to lie within this range. So for the case where I've clubbed these two elements and the rest three elements, so the case I'm talking about is let's club these and club these. So in that case, the sum for this subarray would be 9 and the sum for this subarray would be 15, 23. So 9 and 23. So for this, the largest sum in all the subarrays is 23, and we know that 23 somehow lies between 10 and 32. Now 10 and 32 are possible when there would have been no constraint on m. But there is a constraint on m that we have to keep these many subarrays. So 10 might not be possible and 32 might also not be possible. So there is going to be a value between these two values that is going to be the most optimal answer. So there are going to be multiple values between these two values that are going to be the answer. And from all those values, I need to find the least value. So another possibility in this is that we club these three elements and we club these two elements. If we club these three elements, the sum is 14, and if we club these two elements, 10 and 8, the sum is 18. And obviously for this case, the largest sum is 18. So there's 18. So between these two extremes, there are going to be multiple answers, and from all those answers, we need to find the least possible answer. Now that we are thinking in this direction, one possible solution that comes to our mind is, what if we try all the numbers between 10 and 32? What if we try all the numbers between 10 and 32 and see if it is possible to get that sum with m equal to 2? If we try all the possible numbers between 10 and 32 and keep a record of all the possible answers given m equal to 2, then the least answer from all those possible answers is going to be the correct answer, right? Which actually makes sense. So what I have tried to do is that I have tried to form a range within which my answer is going to lie, and within that range I will pick all the elements and try to see that which is the best possible or most optimal answer. So this range is specifying a range of potential answers. So all the answers, all the numbers in this range might not be correct, but they are this represents a potential answer range. And what I need to do is need to check for each element that whether it's an answer or not. And we need, for all the possible answers, I need to find the minimum answer. Now that being said, if we have understood this logic, one thing that we need to observe is that this range is sorted. Now, if this range of integers is sorted, why do I need to do a linear search to find all the possible answers? Why can't I do a binary search in this range? So if you have a sorted range and you are trying to search for something, then linear search might not be the most optimal approach. What you can do is do a binary search. But what would be the logic for discarding the halves if we are trying to do a binary search? So one thing we know is that if we arrive at a particular value, say 23 was the mid, and I try to find whether 23 is a possible answer or not. If I try to find that 23 is a possible answer or not, do I need to check any element on the right side of 23? No, I do not need to check any element on the right side of 23. There might be elements on the right side which would be answer, but 23 in itself is an answer, and obviously 23 is going to be less than all the elements on the right side. If I have got a smaller answer, there's no need to check for larger elements. So that way, if 23 is one of the possible answers, I can completely discard my right side. I still need to continue my binary search on the left side, because there might be a possibility that there's an answer on the left side, and since the elements on left are going to be smaller, there's a possibility if I continue with binary search on the left side, I will find an element which might be an answer, and it will obviously be smaller than 23. Then that element should be returned as the final answer. Now we have discussed that how we are going to discard the right hand side. What will be the case when the left side will be discarded? So if I landed at an element, and I tried to check, is this a potential answer? Is this a possible answer? If this element is not a possible answer, so what does that imply? That there is no way I can break this array into sub-arrays and the largest sum in all the sub-arrays is less than equal to this element. If that is the case, then only I'll say that this is not a possible answer. So if there's no way to break the array into sub-arrays such that the largest sum is smaller than this particular element, will I be able to break this sub-array in such a way that the largest sum is smaller than 18? Obviously not. If I was not able to break it into sub-arrays such that the largest sum was less than 23, how will I be able to break it into sub-arrays where the largest sum is less than 18, given that the value of m is same? because if I increase the number of subarrays, obviously I'll be able to break it into subarrays with a sum less than equal to 18. But given m is fixed and there was no way I could break this into subarray with the largest sum smaller than 23, obviously there's not going to be a solution where I'll be able to break it. So that's why when I find an element which is not a possible answer, I do not need to check on the left hand side. I can discard the left hand side, and that's how our binary search will work. And this application of binary search is widely used. There are so many problems where we come up with a range for the possible answers and then try to do a binary search within that possible range. Now we could optimize it further. So I used a very naive logic to find the limits for this range. So I came up with 10 and 32 and as the limits for this range, and to find 10 and 32 I used a very naive logic. If you can improve the logic for finding the limits, that is 10 and 32, instead of 10 and 32 you could find a more optimal algorithm to find more tighter limits. Your algorithm would be optimized further because binary search would then run on a smaller range. So that is another part of the problem, that we can use a more optimized logic to come up with the ends for the range. But yeah, that is something I'm not really focused on right now, and I'm focusing more on the binary search approach. Now that we have understood the logic, let's try to go through the code for this problem. So this is the code for this problem, and this is our main method split array, which is going to be called by the driver function. And as mentioned in the question, we will have two inputs. One is the number array, and then we have int m, which determines how many sub arrays do we need to break this array into. Now, as we discussed, we try to find the range for binary search. So A and B are representing the range for binary search. So A I have taken as the lower range, and it is obviously going to be the maximum element of the subarray. The lower range cannot be smaller than the maximum element because that maximum element cannot be broken down. So the best possible case is that I put each element in a different subarray and the largest sum is equal to the maximum element. The worst case is that I put everything in one array, so the upper bound is going to be the sum of all the elements. So in this loop I've calculated the lower bound and the upper bound. Now this is the simple logic for binary search. So what we are doing here is that we are calculating the mid of the upper and lower bound. So the very basic logic of binary search. Then we are using a helper function check to determine if mid is a possible answer. So this helper function will return true or false depending on whether mid is a potential answer or not. So as we discussed, if mid is a potential answer, then we do not need to check on the right hand side because we have already got a smaller answer. So the only thing we need to do is continue our binary search on the left hand side. So that's what we have done. We update our answer because this is one potential answer, and as well as continue our binary search on the left hand side. The second case is that when this was not a possible answer. So we have already discussed, if this is not a possible answer, then any element lower than this answer is definitely not going to be the correct answer. So what we do is we discard the whole left hand side and continue our binary search on the remaining right hand side. And once we are done with this binary search, we finally return the answer from here. Now let's discuss our helper function check. So this is the helper function which is taking the original array and it is taking the allowed number of subarrays, and it is taking another input which is called sum, and sum is nothing but the mid value or the value which we are trying to test if it is a possible answer or not. Now okay, so I've named this variable also now. So this variable now basically stores the sum of the current subarray till a particular time. So when I'm at the very first element, the sum of the subarray, the sum of the current subarray till that time is going to be the element itself. And when I'm at the first element, the total number of subarrays till now that I have is going to be 1, because that first element is definitely going into one subarray. So we need one subarray for sure. Now what is the logic of this helper function? So this helper function is basically following a greedy approach. So what we are trying to do is that we are trying to keep the number of subarrays as minimum as possible. Now this input sum, which we are trying to test if it is the potential answer or not, if we see, it is kind of an upper bound for us for this problem. Like our sum for any subarray cannot exceed this sum, because if the sum for any subarray exceeds this sum, then this is not a potential answer. This has to be the largest possible sum. So if we are able to break into subarrays such that the sum of each subarray is less than equal to this sum, then we know that this is a potential answer. So what we are trying to do is that we are trying to greedily add each element to a subarray until the sum of the subarray exceeds this given sum. Once the sum of a given subarray or the current subarray exceeds this sum, definitely I have to start a new subarray, because if the sum is going to exceed the threshold, then this confirms that this is not the potential answer. So we'll try to keep the sum of the subarray smaller than this given threshold, and while doing this we'll try to see that how many subarrays we had to take, like what was the minimum number of subarrays we had to take to keep the sum of each subarray smaller than this sum. If we are able to do this, if to do this we required less than or equal to m arrays, so then we can say that given the current threshold of m subarrays, we can actually break this array into subarrays such that the largest sum is smaller than our threshold, and then this implies that this sum is going to be a potential answer. So that is the exact thing which we are doing in this method. For the very first element, we know that the sum of the current subarray is going to be the element itself, and till now we need only one subarray to put that element. Now we start from the second element of this array. Now we check if adding this element to the current subarray will make our sum for this current subarray greater than the threshold. If adding this element to the current subarray still keeps the sum of that subarray less than the threshold, then it makes sense to add the element to the current subarray. So what we have done, if the sum of the current subarray and the current element is less than equal to the threshold, I have added this element to the current subarray. But if this sum exceeds the threshold, then I have to start a new subarray. So what I have done, I have increased the number of subarrays that we require, and the sum for the current subarray is going to be equal to current element, because this is right now I have just started my new subarray and this is the first element that is going in that subarray, and in the end I just return a true or false based on whether I was able to accomplish this task with the total number of subarrays less than equal to my given m threshold. And that's how this helper function helps in checking whether this is a potential answer or not. Now let's discuss the time complexity. So let's assume that the order of each element or each element in this array is going to be less than equal to x, and there are total n elements in the array. So if each element is going to be less than equal to x and there are total n elements, then a is going to be of the order of x and b is going to be of the order of n into x in the worst case. So my binary search is going to take time O of log of nx, and the check function traverses through the entire array, so the check function takes time O of n. So the total time complexity would be, for each operation of binary search we are calling the check function, so the total time complexity would be n into log of nx. Now I submitted the exact same solution on Leetcode, and as expected it was accepted, and these are the stats which I runtime and memory usage stats which I got. So with this I think we are done with this problem, and we have discussed the logic as well as the code. So as we discussed earlier, this approach can be used to solve many problems. So you should go online, find few problems that can be solved using this approach and try to solve them on your own. And in general also, you should go online, maybe on Leetcode, HackerRank or Geeks for Geeks, whichever website you prefer, and try some questions on binary search. Only after doing this self-practice, you'll be able to consolidate the understanding of binary search. And if you still have any questions or doubts, please feel free to reach out. So I guess that's it from my side. See you in the next series. Till then, take care and keep learning. Bye bye.